I think we can continue our session. Now we'll hear a talk of Vladimir Dragović, Integrable billiards and polynomial Pell's equations.
Thank you very much. First of all, I would like to thank the organizers for giving me this opportunity to participate and contribute to the conference devoted to Viktor Matvejević Buchstaber. Drage kolege i друзья, мне очень жаль, что я не смог присутствовать лично. Я вспоминаю сейчас, где-то 35 лет назад, 88 год, на семинаре Новикова, когда я первый раз имел возможность встретиться с Виктором Матвеевичем, который тогда был одним из великих ученых, который семинар Сергея Петровича объединял. Вот в этих течение 35 лет одним из достижений собственных могу сказать то, что считаю Виктора Матвеевича своим другом. Так что мне особенно приятно посвятить эту лекцию Виктору Матвеевичу в связи с его 80-летием. So, okay, I will switch now to English. I added one word which should have been in the title, original integrable billiards, combinatorics, and polynomial Pell equation, to match a little bit more the title of the conference, which connects the fields where Viktor Matvejević produced fundamental results, algebraic topology, combinatorics, and mathematical physics. So this particular talk, somehow something is now not working, is based on a few recent papers with Milena Radnovi, and also one with Milena Radnovi and a famous American specialist in field of combinatorics and special functions, George Andrews. So this is a part of a bigger program which I try to pursue together with my collaborators for the last 20 or 25 years, which connects integrable billiards and Poncelet theorem. Then Pell equations is a monodromic deformations, extremal polynomials, approximation theory, potential theory, and then algebraic curves, Riemann surfaces, and Jacobians. And there is yet another area which I didn't put here in this simplex or tetrahedron. This is the fifth area is combinatorics. So I will try to emphasize some connections with combinatorics, specifically for the aim of this conference. So of course, all of you know better than me what mathematical billiards are. So we assume, of course, that this is a mathematical idealization of a game of billiards. And in this mathematical idealization, we forget about all these nice features which real game of billiard make interesting. So we don't assume any friction, we don't assume any spin and things like that. Still, as we know, mathematical billiards are a very fruitful playground to investigate many important mathematical features. So the only, of course, the main characteristic is that we have two regimes. One is, let's say, motion, let's say, under inertia on the table, and then when the particle reaches the boundary, then there is the second regime. This is reflection of the boundary, and we assume this geometric law that these two angles are equal. And we are going to talk about integrable cases, which we know are related to quadrics. And usually the main body of work in billiards is related to planar cases, two-dimensional cases. In this talk, we are also going to talk about high-dimensional integrable situations. So we are going to talk about billiards within quadrics. In particular case of in the plane, we have this a very well-known situation, famous situation of a billiard within ellipses. And we know that it has three main regimes. It has three regimes. Two main regimes are presented here. So one would be the regime where the initial trajectory is this red one, which does not intersect the segment defined by focal points. And then after reflection, we again get such a segment which does not intersect the segment defined by focal points. And in this red regime, there is this is a theorem, there is a caustic, there is a curve confocal with the boundary, this dotted ellipse, red one, which touches every segment of such a trajectory. So this is a caustic, this is manifestation of the existence of additional first integral. There is a second main regime. This is this blue regime where this initial trajectory intersects the segment defined by focal points. And then after reflection, again, we will be in the blue regime. It will intersect this segment defined by focal points. There is, of course, a borderline regime, which is not presented here when this is passing through focal points. But in this blue regime, we have this dotted hyperbola confocal with the boundary, which is a caustic, which then has this property that either trajectory or the segment of trajectory or the line which contains the segment touches this hyperbola. So both these confocal caustics, dotted red ellipse or blue dotted hyperbola, are that manifestation of the existence of additional first integral. Here, what we see is that one particular small observation, which we will use later, is that these segments of blue regime intersect this x-axis. So they intersect, each segment intersects this segment defined by focal points. And this is related to a very famous result from obtained on Russian soil by French mathematician Jean-Victor Poncelet in 1813, which said that if you have a situation that you have two conics, which are not necessarily confocal, and then if they are such that starting from one point, from let's say outer conic, you tangent the inner one and then intersect the outer one in the second point, then tangent the inner one, and so on. If this comes to initial point after few steps, let's say here 3, then starting from any other point from the outer conic and playing the same game, you will come to the initial point in the same number of steps. Of course, for the game of billiards, then we see that if you have a boundary and a caustic, which produce one periodic trajectory, then any other trajectory with the same boundary and the same caustic would produce the periodic trajectory with the same period, which can also be seen, of course, in the case of integrable systems in general, from also different perspective and using different arguments. So, but what is our goal? Our goal is for any dimension d and any period n to classify all periodic trajectories within ellipsoids in d-dimensional space of period n. And what is going to be apparent, we are going to use one new or novel topological, novel combinatorial object, which we are going to call billiard partitions, which are going to codify these periodic trajectories. But of course, when we talk about periodic trajectories and classifying periodic trajectories, we should actually reformulate the question, and instead of asking about periodic trajectories, we should ask about, with a given boundary, about caustics which generate periodic trajectories. Because with one given caustic, as you see here, and according to Poncelet theorem, you have infinitely many periodic trajectories. So in a sense, this is the caustic which codifies this situation that we have periodic trajectories, in this case of period 3. So what we are going to describe actually is using this new combinatorial object called billiard, which we call billiard partitions. We are going to codify for a given boundary caustics which generate periodic trajectories of a given period. So very simple example of such a result. So suppose that we talk about planar case, and we talk about the simplest case. These are two periodic trajectories. Two periodic trajectories are trivial. They belong to coordinate axes, either x-axis or y-axis. We have these two periodic trajectories. But this is going to be a sort of a trivial case where the trajectories lie to sort of a coordinate axis or coordinate hyperplane in higher dimensions. But sort of a more generic, the simplest situation is these three periodic trajectories. And we can see here easily that for three periodic trajectories in the plane, the caustic is always an ellipse. It cannot be hyperbola. So how can we prove this easily in one step? You remember I told you that in this blue regime, which has hyperbolas as caustics, every segment of this is I mentioned this here, every segment has to intersect the x-axis. So if trajectory is periodic, that means that after n steps, it needs to come to the original point. That means that x-axis in this blue regime has to be crossed even number of times because you need to come back. So that means that if hyperbola is a caustic, periodic trajectory has to have even period. So that means that if it has odd period, as the periodic trajectories have, that means that the caustic has to be an ellipse. Now, let's go to higher dimensions. And in higher dimensions, of course, we can easily imagine that we work in some eggshell. Let's say in some space station, there is an eggshell, and these astronauts are playing billiard within this shell. So the boundary is an ellipsoid, and then trajectory is moving within the ellipsoid according to like a straight line motion, uniform motion. And then when they reach, then the particle reaches the boundary, then of course it's easy to see that you can equally easily define reflection, and you have this geometric law of preserving this angle of impact and this outgoing angle. But let's think for a moment about three-dimensional case. How many caustics do we have in three-dimensional case? This is the question. So apparently, if this is a billiard within an ellipsoid, then among confocal quadrics, there will be two confocal quadrics which are going to be caustics for a given billiard trajectory, meaning that every segment of billiard trajectory or the line which supports it is going to be tangent to two quadrics from this confocal family generated by the boundary ellipsoid. And similarly, when we go to d-dimensional case, to d-dimensional space, we have ellipsoid, which is a hypersurface of a quadratic hypersurface of dimension d-1. Then they are going to be d-1 quadrics from confocal family generated by this ellipsoid, which are going to be caustics. So in a sense, as dimension grows, the number of caustics also, the number of caustics grows, which corresponds, of course, to this situation of integrability that as a configuration space grows, then the number of integrals is needed to grow equally to have a complete integrability. So, so now we started this investigation with Milena Radnović by trying to describe in d-dimensional space d+1 periodic trajectories first. So that was our goal. We had the feeling that there is some sort of uniqueness of caustics generating d+1 periodic trajectories in d-dimensional case. So first I need to introduce this simple but important notion of essential and non-essential trajectories. So non-essential trajectories are going to be those, if you're talking about billiard in d-dimensional space, non-essential trajectories are going to be those which can be placed in coordinate hyperplane. So that means that if we can place them in a coordinate hyperplane, then we can study them as examples of situations of d-1 dimensional space and so on. So in a sense, we want to, we consider essential trajectories, talking about d-dimensional space, those which cannot be placed in hyperplane in any hyperplane. That would be the proper definition. The first thing which we're going to show is that, I mean, one of the things which we're going to show is that the essential trajectories with the smallest period are d+1 periodic trajectories. And then we're going to show that in terms of caustics, this is going to be a unique situation. The interesting thing is that the main tool in this investigation is going to be the theory of extremal polynomials. So theory of extremal polynomials is going to provide what is needed to investigate this situation. So, but let me give this definition of confocal family of quadrics in d-dimensional space. In plane, this is easy to define geometrically. We can take two points and say we consider all ellipses and hyperbolas which have which share these 2 points as focal points, and then we can also add coordinate axes as degenerate conics belonging to this confocal family of conics in the plane. In higher dimensions, this geometric description is not that transparent anymore, but we can remember the algebraic form of definition of confocal family in the plane, and then easily generalize this to confocal family in any dimension. So we are getting this family of quadrics for different real parameter lambda. So we assume that A1 to AD are real and distinct coordinates given, and then for various lambdas, we are getting, for each lambda, we are getting a quadric, and these quadrics with each for a given lambda give a family of confocal quadrics. So for each now fixed for fixed point with Cartesian coordinates x1 to xd, then we can do opposite. We can then solve this equation with given x1 to xd and given a1 ad as parameters. We can solve for lambda, and we get solutions lambda 1 to lambda d, which parameterize these d quadrics from confocal family which contain this point with Cartesian coordinates x1 to xd. So here we have a three-dimensional picture. We see an ellipsoid, which is a representative of ellipsoids from this family. Then there is one one-sheeted hyperboloid and one two-sheeted hyperboloid. And for example, they intersect in this point here. So this point here has Cartesian coordinates x1, x2, and x3. And to this point, there are three parameters, lambda 1, lambda 2, and lambda 3, which lambda 1 represents this ellipsoid, lambda 2 represents this one-sheeted hyperboloid, and lambda 3, two-sheeted hyperboloid. And these coordinates are Jacobi coordinates. They're introduced by Jacobi in his famous lectures on dynamics, which he gave in 1842, 1843. Luckily, these lectures got published by Klebsch after Jacobi's death in 1865. Jacobi died in 1851. So some 14 years after, these lectures got published. And thanks to that effort of Klebsch, we still have this opportunity to enjoy reading about this beautiful and deep course organized by Jacobi back then. He used, of course, Jacobi coordinates, as we know, to solve one of the most important open problems of that day, coming from integrable systems. This is to integrate the problem of geodesics on the ellipsoid. So this is the result of Jacobi's lectures, 1842-1843, using Jacobi coordinates. But as a great master of pedagogy, Jacobi, in his 26th lecture, where he introduced Jacobi coordinates, and before solving this main problem he wanted to deal with, of geodesics on ellipsoid, he did one trivial exercise. He integrated the equation of a straight line. He integrated the equation of straight line in Jacobi coordinates, and what you see here, this is the system of equations which derived by Jacobi to integrate the equation of free motion, if you want, but this as a result gives the straight lines. So what we have here is underlying, these are of course given in terms of hyperelliptic differentials and hyperelliptic integrals, and there is underlying hyperelliptic curve. So A1 to AD are the parameters which describe confocal family of quadrics, and then for every line, for each line, there are d-1 quadrics from confocal family which are tangent to this, to this line. These are those d-1 quadrics which are going to play a role of caustics in our billiard problem. So suppose that, so A1 to AD are given in advance. These are parameters which define our confocal family of quadrics. And then by picking a line, we pick d-1 quadrics which are caustics to this, which are tangent to this line from belonging to confocal family. Now, we can consider now the family of all lines which have this d-1 fixed quadrics as caustics, and for them, so there is this underlying hyperelliptic curve, which is composed of so d parameters a's and d-1 parameters alphas. So these are these integrals of motion for this uniform motion, and these are also going to be integrals of motion for this billiard reflection, because the theorem is that if you take any quadric from this confocal family as a boundary, then after reflection of that quadric, the new line is going to be tangent to the same d-1 quadrics parameterized by alpha 1 to alpha d-1. In other words, the family of lines which are tangent to the same d-1 quadrics, this family of lines is invariant with respect to billiard reflection of any quadric from confocal family. So, and then what we want to understand deeply and fully is behavior of Jacobi coordinates. So we introduced what are Jacobi coordinates on one of the previous slides, and then we have now our ellipsoid, we have a confocal family, we have attached Jacobi coordinates, and we consider a periodic trajectory which has certain fixed caustics. D-1 caustics are fixed, and then we want to see how the elliptic coordinates behave along this period. So what we can see is that each elliptic coordinate, and there are d of these coordinates. So each coordinate has its own segment in which this coordinates goes along the segment from one endpoint to another and then back. But it goes monotonically. It's not that it goes a little bit, then stops, then a little bit back, and no. It goes monotonically from one endpoint of the segment to another endpoint, then monotonically back and forth, back and forth, back and forth. So there are these D boxes in the intervals, and in each interval, corresponding Jacobi coordinate operates. So what are endpoints? What are these endpoints? What are these endpoints of these segments? And we can see that these endpoints, these endpoints are: one point is reflection of the boundary ellipsoid. D minus 1 points correspond to touching of a caustic, and D correspond to crossing through a coordinate hyperplane. So we have these segments have 2D in general, in total, 2D endpoints. These 2D endpoints is one endpoint corresponds to reflection of the boundary ellipsoid. D minus 1 points correspond to touching a caustic, and D correspond to the moment when our trajectory penetrates through coordinate hyperplane. Of course, now, as we know, as it's usually the case in integrable systems, they can be traced and linearized on the Jacobian of corresponding curve. Here, this is Jacobian of this hyperelliptic curve which I introduced, and then this motion can be traced as a linearization on this Jacobian, and we have this relationship which corresponds to billiard motion. And then we are getting these coefficients where A, of course, corresponds to Abel-Jacobi map. And then we are getting these coefficients, which are some integer numbers. And then what we introduce then up to a sign. So in a sense, positive absolute values of these numbers, we are going to call the winding numbers of the given and periodic billiard trajectory. But this zeroth winding number is the period of billiard trajectory. So now the question is about this. So we have 2D minus 1 parameters. We have D parameters A's, which come with the confocal family, and we have D minus 1 parameter alpha 1 to alpha D minus 1, which correspond to caustics. And we can assume, for example, that A's are ordered. A1 is smaller than A2 and so on. We can assume that alphas are ordered. Alpha 1 is smaller than alpha 2 and so on. But the question is, what is a order between sum of alphas and sum of A's? So now let us denote B's, the union of A's and alphas, and let us assume that B's are ordered. So B1 is the smallest, B2 is next one, and so on. Unfortunately, I will also need reciprocal values. So I will introduce C's as reciprocal values of B's, and C2D I will denote as 0. And then there is a very interesting and important result of Michel Audin. Now it's going to be soon 30 years of that, which tells us about the mutual order between A's and alphas in the following way. So if alphas are ordered, then J alpha is either B2J minus 1 or B2J. So in a sense, we have some freedom in choice of where J caustic is going to be placed. We have a freedom, but we have a small freedom. So in a sense, this is a good example of this well-measured freedom. So in a sense, there is some freedom, but not too much of that. And this is what we are going to exploit. So I call this, I will refer to this as Audin alternative, or maybe I will use this AA to denote this result. In particular, the largest one is AD. So A's are these parameters corresponding to confocal family, and they correspond each to a coordinate hyperplane, and alphas yet again are correspond to caustics. So the largest B is AD. It cannot be alpha. So the largest B is AD. And now, we come to one important moment, and I'm referring now to my proof, which I gave you, that for 3 periodic trajectories in the plane, the caustic had to be an ellipse. Because I told you that if we had this trajectory with hyperbola as a caustic, then each segment had to intersect x-axis even number of time if this is a periodic trajectory. So that had to be even period. A period had to be even if hyperbola is caustic. Now, using the same argument, if we have a periodic trajectory, and if we want to see how many times a periodic trajectory penetrates through a coordinate hyperplane denoted by AJ, for periodic trajectory, this has to be even number. So if if we have a segment which during the period, our corresponding Jacobi coordinate passes odd number of times, then both endpoints have to be caustics. Both endpoints have to be caustics, because what I just said, if one of the endpoints would correspond to coordinate hyperplane, so to A, then this has to be even. So if the winding number, this is my first observation here, if the winding number Mj is odd, then both endpoints, corresponding endpoints, have to be from the caustic set. But from here, and this odd and alternative telling us that J caustic has to be either B2J minus 1 or B2J, we see that we cannot have 4 consecutive among B's, we cannot have 4 consecutive B's which correspond to caustics, because this will be violated. Odd and alternative will be violated. That means, in terms of winding numbers, the 2 consecutive winding numbers cannot both be odd. So if we have one winding number which is odd, then the previous one and the next one have to be even. And from the fact that this B2D minus 1 is AD, is A, that means that this MD minus 1 winding number has to be even, because it corresponds to AD. So here we are getting sort of we are going toward axiomatization of partitions which we are going to use to classify periodic billiard trajectories and their caustics. Is there any question about this? Okay, if there are no questions, then let me first say that for in d-dimensional case, the fact that all trajectories of period smaller or equal d have to be placed in a coordinate hyperplane, this is a consequence of Riemann-Roch theorem. Because Riemann-Roch theorem tells us, I mean, this can be translated on algebra geometric language, and then in order to have a billiard trajectory of a given period, we need to have a certain amount of functions on this hyperelliptic curve with certain properties, which I'm not going to describe. But the fact is that in Riemann-Roch theorem, we have that the dimension of this space of functions with the prescribed singularities given by divisor D is given by, I mean, for the divisor of degree big enough is degree of D minus genus plus 1. And here, dimension and genus dimension D and genus G are related that G is equal to D minus 1. So in a sense, if degree of D is not big enough, then G needs to go down, and that means the dimension needs to go down. This is a sort of hand-waving application of, but this can be formalized fully. That how Riemann-Roch theorem tells us that in D-dimensional case, if you have a D-periodic trajectory or a trajectory with period smaller than D, this has to be placed in sum of coordinate hyperplanes. So now, what about D+1 periodic trajectories? D+1 periodic trajectories, then we can see easily that we have in this case, we will have this integer part of D-2 or D-1 over 2 pairs of the same type of caustics. And in case if D is even, then we also have an ellipsoid as a caustic. And of course, there is a way to codify the situation, which actually corresponds to the fact that there is a point of a finite order on the Jacobian of this hyperelliptic curve. And in a planar case, these are famous Cayley's conditions, which are written in terms of determinants of made by coefficients of the expansion of this elliptic curve in the planar case. So together with Milena many years ago, 20 years ago, we generalized this condition as a rank condition on rectangular matrix for higher dimensional situations. Now, I mean, relatively soon later, I realized that we can rewrite this in these terms of Pade approximation condition for polynomials of degree m and degree m minus d. However, it needed more than 10 years for us to understand how to properly use this equivalence. So of course, what we knew immediately is that then this condition, of periodicity of billiard trajectory, because it's rewritten now in this form of Pade approximation for polynomials, can be rewritten in terms of Pell's equation, polynomials Pell's equation, where this polynomial, so what is a polynomial Pell's equation? This is equation of the form square of a polynomial minus some polynomials times square of another polynomial equal 1. So this coefficient polynomial in the middle, this one, the only one which is not a square, this is obtained as the zeros of this polynomial are endpoints of segments of in our case of these segments on a real line. But it is very difficult. It is very rare that a union of the intervals which codify this polynomial p hat is going to allow a solution of Pell's equation. So, and then these polynomials which appear as solutions of Pell equation are polynomials of very special properties, and I'm going to talk about this a little bit later. So these are extremal polynomials. And the prototype of such polynomials are Chebyshev polynomials, which for the case of one interval were introduced by Chebyshev. So so we have this now. We are coming from description of periodic trajectory. We are coming to Cayley type condition. From Cayley type condition, we are coming to Pade approximation type condition. From there, we are coming to this Pell's equation. Let me introduce one more object, one more notion. This is the signature related to Pell's equation. So tau j is the number of zeros of qn minus d in certain intervals. So in interval c2j minus 1, the number of zeros of q we will going to denote by tau j. So let me remind you that cj's were reciprocal to these BJs, and BJs were unions of A's and alphas. So what are Chebyshev polynomials? So we all know, and here I made a brief reminder. So for example, here is a Chebyshev polynomial of degree 6. Here is Chebyshev polynomial of degree 9, defined on interval -1, 1. You see this beautiful oscillation going from this 0.1 over -1, then monotonically down. Then here we have this critical point, so going then up monotonically. So this is -1. So it oscillates monotonically from 1 to -1 and back. And here we have these two situations of even and odd degree. So the Chebyshev polynomials, as we know from Chebyshev, are solutions of Pell's equation, where this interval -1, 1 comes as this coefficient interval polynomial x minus 1 times x plus 1. And then if we normalize these Chebyshev polynomials to get monic polynomials, then we know that these are the monic polynomials of given degree, which minimize the uniform norm on the interval -1, 1. So these are Chebyshev polynomials. This is case of one interval, and this is a Pell's equation in this situation. Of course, Chebyshev is a great mathematician. He had also excellent students, and one of them was Zolotaryov, who generalized this situation for the case of two intervals. So the task is to find a monic polynomial of degree n, minimizing the uniform norm of the union of two intervals. And then if we denote solution of such a as Pn hat and its norm as Ln, then the question is, would this polynomial be or divided by Ln, would this be a solution of Pell's equation? So we have a polynomial Pn, which is a solution of this min-max problem on union of two intervals lambda 1, lambda 2, union lambda 3, lambda 4. The question is this going to be a solution of Pell's equation, where this coefficient polynomial, lambda minus lambda j goes from 1 to 4, comes from these endpoints of these two intervals. And the situation is not the same as in the case of one interval. In the case of two intervals, the situation is much more subtle. So you start with any two intervals, and you can find a monic polynomial of degree n, which is going to solve this min-max problem. You can do it. But then maybe the situation is such that you can extend and enlarge a little bit these two intervals. But this polynomial you got as solution of min-max problem stays a solution of this change problem when you deform a little bit intervals. And if you produce this procedure further and further, as much as you can, you will come up with maximal two intervals for which this polynomial is going to be the solution of this min-max problem. Only these maximal intervals are going to produce solutions of Pell's equation. So in a sense, unions of two intervals, which are sort of supports of polynomial of Pell's equation, are very special. And similarly, this can be extended to the union of D intervals, and the situation is similar. So in a sense, it's very rare for union of D intervals to be such that there is a polynomial Pell equation solution in which this polynomial coefficient is going to be given by polynomial lambda minus lambda j, where lambda j are endpoints of these D intervals. So here is one example of Zolotaryov polynomial over intervals lambda 1, lambda 2, and lambda 3, lambda 4. And you see similarities with Chebyshev polynomials. It goes from -1 to 1 monotonically, then back. Here is a local maximum, then goes back monotonically to -1. So over the interval -1, 1, it starts at -1. Here it ends at -1. And then there is a gap interval, lambda 2, lambda 3 is gap interval. And this polynomial goes outside the strip -1, 1 here, and then goes back to this 3 at lambda 3, and on lambda 3 to lambda 4 goes monotonically from -1 to 1. So in a sense, what you can see that union of these two intervals, lambda 1, lambda 2, and lambda 3, lambda 4, is nothing but inverse image of this polynomial of interval -1, 1. So union of two intervals, which allows solution of Pell's equation, has to be inverse polynomial image of interval -1, 1, showing how difficult it is for two intervals to be the supports of this polynomial Pell's equation. So similarly, we can extend these to D intervals, and we will call these generalized Chebyshev polynomials. And then there is one object related to this extremal polynomials. Is called points of alternance. I think Borel was the first who wrote about this in 1905, at least the first written record. And I think the same year, I think it was Markov who also had this in his lectures. I don't know if there is some trace prior to 1905 of mentions of points of alternance. So what are points of alternance? So subset of the solutions of the equation, this extremal polynomial square equal 1, with maximal number of elements, such that the signs of Pn altered on it is a set of alternance. And then such set is not uniquely determined. However, the number of its elements is fixed and is equal to n plus 1. So here, so these are points where this interval this polynomial takes either -1 or 1 as values, and it has to take alternatively. So we can take this point here, for example, as 1 in this case, it takes value -1. Then here it takes value 1. Here it takes value -1. Then this one we have to skip because it will be again -1. It doesn't alter. But then this one it takes value 1. So we can take this point, and this point, and this point as alternance set. Or alternatively, we can skip this one and go here. But anyway, this is what it is. These are points of alternance. And then using the properties of points of alternance, and specifically the result of Crane, Levin, and Nudelman, we managed to prove the following theorem. That these winding numbers satisfy the following relation, that mj is equal mj plus 1 plus tau j plus 1. So tau j is number of zeros of polynomial q on jth interval. And in particular, we show that these winding numbers satisfy this inequality. So the first winding number, zeroth winding number, is the largest, then the second is the second largest, and so on. So in this way, we managed to prove this relationship, which was one of the three conjectures of Ramirez-Ross from 2014. And actually, by using this technology, we proved affirmatively all four conjectures of Ramirez-Ross. And this gives us the tool how to fully classify all these periodic trajectories. So my time is a little bit going. So what I want to say is that by using these properties that I told you, that two consecutive winding numbers cannot be both odd, that the last one has to be even, and we are getting this inequality, we turn out to description of periodic trajectories, or caustics which generate periodic trajectories, to investigation of combinatorial object, which is we call billiard partition. So I'm going to now fast forward a little bit. And so we are coming to these Euclidean billiard partitions. And I quoted here a statement from Israel Mesievich-Gelfand, who said, the older I get, the more I believe that at the bottom of most deep mathematical problems, there is a combinatorial problem. So we reduce now this problem of study of periodic billiard trajectories to study of integer partitions with the following properties: that the smallest part is even, adjacent parts are never both odd, These are the axioms. And apparently, I discussed this with George Andrews, who is a leading expert in theory of partitions, world expert, and he got enthusiastic and interested in it. I thought it's going to be something very well known, but for him, he saw some novelty here. So we then started to investigate this. We also added weights in these partitions, which correspond to number of options given by odd and alternative, which would give these weights to these partitions. I don't have time to tell you more about these weights, but they come from odd and alternative. And then the idea is that together with these billiard partitions, we can also consider so-called base billiard partitions, which have the property that the smallest part is 2, adjacent parts are never both odd, and then the difference between adjacent parts is at most 2. And then we show that every this billiard partition can be uniquely presented as an element of this base set D bar, and a partition which has only even components. And then using the machinery of theory of partitions, we are getting generating functions for these partitions. So this is sort of a connection between combinatorics and integrable billiards as a part of mathematical physics. So these are these formulas, and here are some further results, because my time is going out. So here is something which I like to mention in this context, because we saw that this Pade approximation here plays important role in study of integrable systems, and somehow integrable systems we don't always connect with approximation theory. Here is this statement from Bertrand Russell that although this may seem a paradox, all exercise is dominated by the idea of approximation, and when a man tells you that he knows the exact truth about anything, you are safe in inferring that he is an inexact man. So at this nice point, I would like to congratulate dear Viktor Matvejević, dragoj Viktor Matvejević, želaju many happy returns, želaju mnogo sreć i uspehov vas i vaših učenikov. Sve vam dobro. Спасибо.
Thank you very much, Vladimir. Let's thank the speaker. Does anyone have questions? So no questions. Let's.
Володя.
Здравствуйте, Виктор Матвеевич.
Thank you very much for the very beautiful talk. I was happy to hear you, see you, and as you know, we start work with you in the topics related to n-valued groups. And certainly, days of and won't result in the series of n-valued groups. You see?
Yes.
Thank you very much for your talk.
Thank you.